Let's now focus on the inhibition of enzymes. We have seen how enzymes typically work. If they interact with the substrate, form the enzyme substrate complex, and then you form the products. Very ideal situations. However, life is not ideal. There are so many other factors that would inhibit the activity of the enzymes. We have already discussed the factors that affect proteins in general. So all those factors affect the the tertiary structure of enzymes. So anything that denatures proteins would denature enzymes. But there are other factors to consider in this section, which again, just the inhibition of the enzymes does not necessarily involve the denaturation of the enzyme itself. But before we move on, let's first define irreversible inhibitors. These are substances that cause inhibition that cannot be reversed. Here, it usually involves formation or breaking of covalent bonds to or on the enzyme. Okay? So here, again, you permanently damage your enzyme. You permanently change the shape of your enzyme. So it's no longer able to accept the substrate into its active site, and therefore no conversion into products. Reversible inhibitors, this is our subject. Here, this is a substance that can bind to an enzyme, inhibit it, but it can be released. So we look at a few types. Competitive inhibitor. This binds to the active site, the catalytic site, and blocks access to it by the substrate. A non-competitive inhibitor, on the other hand, binds to a site other than the active site, but it inhibits the enzyme because it changes the conformation at the active site. Okay, there's actually also a third class, uncompetitive inhibition and mixed inhibition. So visually speaking, okay, so if you have a competitive inhibitor, it binds to the active site, preventing the substrate from binding to that active site. On the other hand, you can have non-competitive inhibitors, also uncompetitive inhibitors. They bind to a site other than the active site. However, upon doing so, the shape of the active site cannot be any more complementary to the shape of the substrate. Or maybe it just doesn't make it as efficient as it should be. Okay, so that's how it prevents the substrate from being converted into products. Okay, competitive inhibition. So the expected situation is, again, you have the enzyme, and this is the active site for your enzyme. There's an equilibrium between the enzyme and the enzyme substrate complex, again governed by the equilibrium constant K sub S. Reminder, the product is formed from the enzyme substrate complex. It's only when you form this complex that a product can be formed. In the presence of a competitive inhibitor, there's an equilibrium between the free enzyme and the enzyme inhibitor complex. Okay, so again, this is the active site, and your inhibitor, okay, binds to the active site, governed by its equilibrium constant K sub I. And since the substrate competes with the inhibitor for the active site, okay, no product can be formed because the presence of the inhibitor prevents the formation of the ES complex, which, again, I emphasize, is the prerequisite for the conversion of the substrate to the product. Okay, so here's another visualization of competitive inhibition. Okay, so you have the enzyme and then the substrate shown in blue. There's an equilibrium between the free enzyme and the free substrate to form the ES complex. Once the ES complex is formed, the product is formed, okay, releasing the new free enzyme, which can take up another substrate. However, in the presence of an inhibitor, then the inhibitor binds to the active site, prevents the substrate from coming in. So the rate of the reaction is now slowed down. Okay, so highlighted here in red is the regular Michaelis-Menten mechanism, enzyme plus substrate in equilibrium with the enzyme substrate complex, and then it forms the product. However, in the presence of the inhibitor, another equilibrium complicates this equation. Okay, so the presence of the inhibitor essentially reduces the concentration of your enzyme that's available to the substrate. We can write a dissociation constant Ki for the enzyme inhibitor complex. Okay, so again, this is just this. Okay, that's recall you should be able to write this from your analytical chemistry and writing KEQ expressions. Okay, so let's look at the mathematics. In the again, this equation is the regular reciprocal of the Michaelis-Menten equation, but in the presence of a competitive inhibitor, the equation changes, and it changes by this factor. So we introduce another term into our Lineweaver-Burke equation. Okay, this just changes now. So for kinetic data, then we will keep the concentration of the inhibitor constant, and then Ki is a constant. Therefore, all these things are constants. So what is the effect? If you look at the line, it's still an equation of a straight line. However, your slope has changed by this factor. Okay, so the y-intercept does not change. Therefore, the Vmax is not changed. Okay, so here's now a plot of the enzyme kinetics for competitive inhibition. So the blue line represents the absence of an inhibitor. This is what we learned in the previous sections. Now, let's run another set of kinetic data, but this time we add some concentration of inhibitor. Again, reminder, concentration of the inhibitor, concentration of the enzyme, temperature, and all other factors in the experiment should be kept constant. So if you do that, it now generates this green line. And if you double the concentration of your inhibitor, then you also change the slope differently. Okay. But its characteristic behavior is that the reciprocal will not change if your inhibitor is a competitive inhibitor. The effect of competitive inhibitors can be overcome by increasing the substrate concentration. So again, it's a little bit descriptive. It's a competitive inhibitor, so they both compete for the active site. So whoever is present in a greater amount will have a higher probability of interacting with the active site of the enzyme. So if ever you have a competitive inhibitor present, then you can be overcome by increasing the concentration of the substrate. Okay. So how does that do that? Okay, well, if we once again go back to the mechanism, we say that the substrate has a complementary shape to the active site. Therefore, the competitive inhibitor should also have a complementary shape to the enzyme active site. So competitive inhibitors usually resemble the substrate. For example, the antidote to methanol poisoning is to ingest ethanol. Okay, by the way, now methanol is toxic. If you ingest methanol, it can cause blindness. So if ever somebody has ingested methanol, one way to combat that is to introduce ethanol. Okay, so in other words, increasing the amount of the substrate can mitigate the effect of the inhibitor. Now let's move to non-competitive inhibition. Okay, so pictorial representation, this one is from your text. I got this from somewhere else. So what happens? Again, once again, we have the usual case. We have the enzyme in equilibrium with the substrate forming the ES complex. However, the enzyme can also bind to the inhibitor, but binding of the enzyme to the inhibitor does not prevent the substrate from binding to the enzyme itself. However, in this shape, no product can be formed. Okay. Also, once the substrate has bound to the enzyme, it also does not prevent the inhibitor from binding. However, just a very important point, the product can only be formed from the enzyme substrate complex. Okay, so these are just different ways of representing the same reaction. Now, what happens here? In this form, the maximum velocity, okay, so given here Vmax raised to the power I for the inhibitor, has the form Vmax divided by 1 plus uh, inhibitor concentration divided by Ki. So in other words, the y-intercept will be changed. Okay, because the inhibitor does not interfere with the binding of the substrate to the active site, Km is unchanged. And in this particular case, even if you increase the substrate concentration, you cannot overcome the effect of the non-competitive in the presence of the non-competitive inhibitor. Okay. So mathematically, okay, again, this is the equation, the reciprocal of the Michaelis-Menten equation. And in the presence of the non-competitive inhibitor, okay, the slope is changed by a factor 1 plus I over Ki. Vmax is also changed by the same factor. So the slope is changed, the y-intercept is also changed. So this is now the line that we will see. Okay, this is for the uh, Lineweaver-Burke plot without the inhibitor, and then with the inhibitor, the slope has changed. The y-intercept has also changed by the same factor. Okay. So if you want to determine Vmax, just determine the Vmax from the uninhibited reaction. How do you now determine the Km? Again, just determine the Km from the uninhibited reaction. Another way, okay, and if it's really a true non-competitive inhibition, the two lines should intersect at the x-axis. Okay, so this is just another look at that equation or that line. So I think I'll just move on. Uncompetitive inhibition. For the uncompetitive inhibition, the inhibitor can bind to the ES complex but not to the free enzyme. Okay, so once again, we have this enzyme and the substrate having an equilibrium to form the enzyme substrate complex, and then you form the product. Again, that's the regular mechanism for the enzyme catalysis, enzymatic catalysis. But in the presence of a uncompetitive inhibitor, the inhibitor binds to the enzyme substrate complex. No? It does not bind to the free enzyme, it binds to the enzyme substrate complex. So what is the effect? Well, Vmax is decreased, Km is also decreased. And we will not go through the mathematics anymore, but in this case, the Lineweaver-Burke plot for uncompetitive inhibition will result in parallel lines. Okay, so visually, this is what you will get. And then let's complicate our lives a little bit more. You can also have mixed inhibition, wherein your inhibitor can bind through a mix of the previous mechanisms. Effect Vmax is decreased, Km can be increased. Lines for the uninhibited and the inhibited reactions intersect usually in the second quadrant, no? Not the x-axis and not the y-axis. So in that case, you have mixed inhibition. We will not go through the mathematics of this anymore. So just a comparison of the types of inhibition: competitive inhibition, non-competitive inhibition, and uncompetitive inhibition. Here, Lineweaver-Burke plot, okay, shows the two lines intersecting at the y-axis. Here, the two lines intersect at the x-axis, and for uncompetitive inhibition, the two lines are parallel. Okay, so let's have another practice session. Let's determine the Vmax, Km, and the type of inhibition for an enzyme given this kinetic data. Okay, so substrate concentration, Vu means uninhibited enzymatic reaction series, and Vi means inhibited reaction series. Okay, so copy the data, take your graphing paper, and plot both the Michaelis-Menten plot and the Lineweaver-Burke plot. So what do we expect to find out? Okay, for the Michaelis-Menten plot, we'll see if the enzymes follow Michaelis-Menten kinetics. Reminder, the curve should be hyperbolic. If the curve is not hyperbolic, then your enzyme does not follow Michaelis-Menten kinetics. It will be useless to do the next step, which is to do the Lineweaver-Burke reciprocal plot, because you will not get straight lines. As mentioned, if the enzyme follows Michaelis-Menten kinetics, then we can deduce a type of inhibition depending on where the inhibited and uninhibited lines intersect, or if they intersect at all. Okay, so reminder, lines intersect at the y-axis means that the inhibitor is a competitive inhibitor. If the lines intersect at the x-axis, then the inhibitor is a non-competitive inhibitor. If you get parallel lines, then the inhibitor is an uncompetitive inhibitor. And if you get something aside from the previous three, then we'll just say it's mixed inhibition. So here's the kinetic data once again. Okay. So if you've done it, this is what expected results should be. Okay, so again, we have the Michaelis-Menten equation. We have the kinetic data. Once again, we plot V versus substrate concentration and also the inhibited rate of the reaction versus the substrate concentration. So we get this. Once again, do you get information like for the Vmax? Where is Vmax from the Michaelis-Menten plot? Is it 120? Is it higher than that? Okay, we don't know. So we do the Lineweaver-Burke plot. Okay, so here we plot the reciprocal of the rate of the reaction against the reciprocal of the substrate concentration and the reciprocal of the inhibited rate of the reaction versus the reciprocal of the substrate concentration. So we get this. So it's already a little bit obvious here that these are parallel lines, okay, for the uninhibited and the inhibited reaction. So we can already say that it is an uncompetitive inhibitor. But we still need to determine Vmax and Km. So we just need the data actually from the uninhibited reaction. Y-intercept is 0.007. So again, extrapolate that. So it should hit the y-axis right here. So it's 0.007, reciprocal of that. is 150. So we'll just run 0.002. Again, I use the Excel to determine that value. So you can just following our significant figure rules, you can just say 150. And then the slope is 0.027 minutes. Or is it minutes? Yeah, I think it's just minutes. Okay, and then solving for the Km, we get 4 millimolar. So again, once again, what is the significance of 4 millimolar? Okay, so my prompt came a little bit early. Significance of 4 millimolar means that if the cellular conditions are such that, again, the concentration of the substrate is less than 4 millimolar, the enzyme is not activated. And if the cellular conditions are such that the concentration of the substrate is greater than 4 millimolar, then the enzyme is activated. So a reminder, just submit your concept maps and your Moodle objectives to our Google Classroom.